Hello, Calculus 3 kiddos. So today we are going to do applied optimization, which is finding relative or absolute extrema, but in context. So the first thing we're going to start with is a geometric interpretation, and then we're actually going to move into statistics. Because I got to be honest, statistics wouldn't exist if it weren't for calculus to be there to back it up. So we'll get to that in a moment. Step one is, let's do this volume example. And again, applied optimization is just, extrema in context. So number one says you have a rectangular box with one base on the xy plane, and a vertex at the origin, and the opposite vertex is on a plane, a slanted plane that goes through the first octant. Find the maximum volume of a box satisfying these conditions. So I'm going to do my best to draw this situation. So there's x, y, and z. And then if I want to sketch this plane, I can actually use the intercept. So when y equals 0 and z equals 0, x would need to be 3 so that equation equals 12. So I'm going to go out 3 on the x-axis. And then I'd go 4 on the y-axis. And 2z equals 12 means I'd go 6 on the z-axis. 1, 2, 3, 4, 5, 6. And so that slanted plane in the first octant would look like that. And what we're going to do is we're going to make a box where one corner of that box is on the plane. So if I think of just a nice example here, like what would be on this plane? You know what would be on this plane? The point 1, 2, 1 would be on that plane. Because 4 times 1 plus 3 times 2 plus 2 times 1 is 12. So if I find the point 1, 2, 1, that'd be like, I don't know, right here. And so I'd be using this box where that dot right there is on the plane. And so I'm basically saying if I were to drag that dot around, it would stretch and shrink the box. I want to figure out where can I put the dot so that the box is the biggest, has the most volume, I should say. All right, so if I want to maximize volume, the volume of that box is x times y times z. And if I want to maximize volume, I want to know when I have, relative or absolute extrema. Well, here's the thing. I've got too many variables right now. And I can reduce the number of variables because x, y, and z can't be whatever they want. In fact, if I were to solve this, this would be the equation z equals 6 minus 2x minus 3 halves y. So my volume in terms of just x and y would be x times y times that z. And if I want to maximize it, I either need to test the corners or test the critical points. Now, if you really think this one through, my restricted domain would be anywhere, like that base corner could be anywhere in that blue shaded region. But the thing is, if I go anywhere near the edge, I don't have a box anymore. So my edge pieces are all going to give me absolute minimum volume. So I know that I want an interior point to find my absolute maximum volume. So I want to find when v sub x and v sub y equals 0. So let me distribute here to make my derivatives a little bit easier. So I'd have 6xy minus 2x squared y minus 3 halves xy squared. V sub x would be 6y minus 4x minus 3 halves y squared. V sub y would be what? 6x minus 2x squared minus 3xy. And I want to know when both of those equal 0 at the same time. Well, I could do that with a system of equations and do it algebraically, but I got to be honest, right now, what I care about is setting it up and getting an answer. I don't really care about the process that much. So I'm going to go to my favorite place, Desmos, because I'm graphing in 2D here. And I'm going to solve this system using Desmos. So 6y minus 4x minus 3 halves y squared equals 0 is that. And then 6x minus 2y squared, minus 2x squared minus 3xy equals 0. Something feels off. Why does something feel off? It doesn't. I'm good. And this would be 3xy. I'm just making sure. You know what, Mrs. Fibber? You did make a mistake. It's over here. It doesn't felt off. The derivative of 2x squared y should be 4xy. Look at that. Found my own mistake. This should equal 0. And this should be 4xy. There we go. I knew these should have been straight. All right, and where do those intersect? They intersect at 1, 4/3. So I get x equals 1, y equals 4/3. And then it's time to find the maximum volume. So I want v of 1, 4/3. And I'm going to let Desmos help me again. So I'm going to define v of xy as xy times, what was it again? 6 minus 2x minus 3/2 y. So there's my volume function. It can't graph it because Desmos can't graph in 3D. But I want to evaluate that at 1, 4/3. And I get 2.6, or 2 2/3, or 8/3. And that is as big as the box can get. Cool. Next, we are going to do statistics. Find the least squares regression line for the points 2, 3, 6, 12, and 9, 29. Okay, so let me show you what I mean by that. So think back to algebra when you did linear regression and you plotted some points. And then you had to draw the line best fit for those points. So if I want to draw the line best fit here, let me see if I can change my axis a little bit. So I want to change my x to like 15. And it looks like that. And so if I wanted to sketch in the line best fit, I've got a line that like comes through here somehow. Maybe if I were to sketch it like, I don't know, like this. I don't know, is that the line best fit? Or maybe that? Or I don't know, maybe this? I don't know. But that line best fit is somewhere in there. And your calculator can do that for you. But the theme of today is, why use your calculator to do something in 25 seconds that you can do by hand in 20 minutes? I'm kind of kidding. It's not going to take 20 minutes, but it is going to take a while. We are going to learn how to do linear regression by hand. So you used to do it on your TI calculator, which is what we are going to do right now for a moment, because then we can check our answer against what the calculator gives us. And so if we want to put it in the calculator, you might remember you have to go to Stat, Edit, and then you need to put your points in a list. So 2, 3, 6, 12, 9, 29 is 2, 3, and 9. And then 2, 3, 6, 12, 9, oops, 12, there we go, 9, 29. And then I can go to y equals, clear out what's in there, go to my stat plot, and turn that on. And then I'm going to go to zoom stat, which is 9, and there's my scatter plot. Okay, so my scatter plot looks like that. And I want to find the line best fit. Okay. So 2, 3, oh, this should say 6, 12. Mrs. Fibber is having so many technological issues lately. Let's try that zoom stat again. There we go. That's more what I thought it should look like. And I need to make my scatter plot. I need to make my line best fit now. So I'm going to quit out of here and go to Stat, Calc, Linear Regression, which is number 4. L1, L2, there's no frequency. And if I want to store my equation in Y1, which I do, I can hit calculate, and I get the line 3.635 and negative 5.932. So y equals 3.635x minus 5.932. Yep. And that should be my line best fit. Let's look and see how that looks. That looks like a pretty good fit in line. But where the heck did those values come from? They came from calculus. So I say again, why do in 25 seconds something in your calculator that you can do by hand in about 10 minutes? And that's what we're going to do now. What we do to get that regression model is we do what's called the least squares fit. And the reason it's called least squares is because we square the residuals. And the residuals are the distance from the points to that line of best fit. So there's 2, 3, there's 6, 12, and 929 would be like up here. And so my line best fit, let's say I didn't know where it was and I thought it was right here. Okay, to calculate the line of best fit, I want to measure these residuals. I want to find the distance from the point to the line, but not the perpendicular distance, the vertical distance. Okay, and those are called residuals. And I want to take those residuals and square them because I technically don't know when they're going to be positive or negative. All right, so how am I going to do that? Well, if I know that this is the point 2, 3, and I know that this line is the line y equals mx plus b, this point right here would still have an x coordinate of 2, but it has a y coordinate of 2m plus b. If this is the point 6, 12, that point is the point 6, 12m plus b. Nope, not 12m plus b, 6m plus b. There we go. Looking at the wrong number there. And then right here, this is the point 929. So this is 9m plus b. I want to reduce the size of those green lines, so I want to minimize this function. I'm going to make a function s of mb, okay? And the reason I'm calling it s is because I'm adding the sum of the squares of the residuals. This distance right here is the residual. It's the difference in the y coordinates. So that's going to be 2m plus b minus 3. Now, I am going to square that because I don't know if the line is above the point or below the point. So I don't know if I was supposed to be subtracting 3 minus 2m plus b or 2m plus b minus 3. So by squaring it, I don't care because it's going to be positive anyway. Then the next set is going to be 6m plus b minus 12 squared. And then the last one, 9m plus b minus 29. All I'm doing is taking the difference in the y coordinates and then squaring them. I want to minimize the value of s of mb. Well, if I want to find the minimum value, I want to find a critical point. So I want to find when s sub m and s sub b equals 0. S sub m is 2 times 2m plus b minus 3 times 2 plus 2 times 6m plus b minus 12 times 6. I'm just doing the chain rule right now. 2 times 9m plus b minus 29 times 9. And I want to set that equal to 0. And then I want to find s sub b, which is going to be 2 times 2m plus b minus 3 times 1. 2 times 6m plus b minus 12 times 1. 2 times 9m plus b minus 29 times 1. And I want to set that equal to 0. And then I want to solve for m and b. Now, we could do this by hand by setting up a system of equations. So what I'm going to do is I'm going to set up the system, but then I'm going to let Desmos help me solve it just to save us a little bit of time. So let's see. Here's the thing. Both these equations are set equal to 0, right? And both those equations have lead coefficients of 2. I'm going to divide both sides by 2 here. Because if I divide 0 by 2, it's not going to make a difference. So I'm going to ditch the 2's, and now I'm going to combine like terms. So I'm going to distribute 2 times 2m, so I have 4m plus 36m, that's going to be 40m, plus 81m is 121 m's, and then plus 2b, 6b, and 9b, that's 17b. And then I have minus 6, minus 72, so I'm at negative 78. And then 29 times 9 is 18, 261. Yeah, 261. So I have 261. And what I say before, 78, which is 339. Woo, those got big. And then S sub B needs to equal 0. So I have 2m plus 6m plus 9m, that's 17m. And then B, 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 3b. And then 29 and 12 is 41. 3 makes that 44. Okay, so I've got a system now that I could solve through substitution or elimination, or just, pull up Desmos and make it help me. So I am going to make Desmos help me here. And let's see, I want to clear everything. There's got to be a better way to clear this, but I'm just going to erase it. So what do I have? I have 121m plus 7b, no, 17b, so it'll be 17y minus 339 equals 0. There's one line. And then 17x plus 3y minus 44 equals 0. And I want to know where those cross, so I'm going to click on it, and it will automatically give me the decimal. 3.635 negative 5.932. 3.635 negative 5.932. Now, why on earth would I make you be so inefficient when I often say, once you've learned something, use the quick way? Well, because when you learned linear regression before, all you know is that your calculator did it for you. You have no idea how it did that. What's really happening is this behind the scenes. You are minimizing the distance between the points and the line. Okay? Another thing I want you to draw from this is before I knew how this worked, I always thought that 3.635 and 5.932 were just kind of like churning through. I didn't know what formula got used to find those. And what's interesting is it's not really a formula that gets used to find those. It's a system of equations. And to me, the really powerful thing about that is that if I were to solve this system algebraically, M and B would both be fractions. In other words, these numbers aren't just some nasty decimal that went through some crazy formula with square roots and all this other nonsense. Those two decimals are both fractions. You have rational solutions to linear systems that involve rational points. And that's pretty darn cool. Okay, so there's linear regression. And I solved this by finding the solution, and I never really wrote it down because it was up there, but we found M and B by solving that system. Okay, this next one is how do you do a least squares regression quadratic? And what I'm going to do here is just kind of explain the work that's in front of you. And then if you want, you can pause this and then type this in yourself. I want to go through with you, though, how to solve this using a matrix. If you want a least squares regression quadratic, what you need to know is that the format for a quadratic isn't y equals mx plus b. It's y equals ax squared plus bx plus c. So when I plot my points and then plot the points that are directly above or below them, okay, like 2, 9 has the point 2 comma something above it, the y coordinate on the parabola would be what I get when I plug 2 into the standard form of a parabola. So if I plug 2 in for x, I get 4a plus 2b plus c, which is why this says 4a plus 2b plus c. So when I go through to find the least squares regression quadratic for this, I'm still going to square my residuals, which is going to be 4a plus 2b plus c minus a 9 squared. And then the next one was 623 and 622. So that point on the regression quadratic would be the point 6, comma 36a plus 6b plus c. So I did 36a plus 6b plus c minus 23. And 36a plus 6b plus c minus 22, because I had two coordinates on that scatter plot with an x value of 6. And then the last point here is 10, 1. So this would be 10, 1, and then this would be 100a plus 10b plus c. Then you take your derivative with respect to a, b, and c, and then you want to solve this using a matrix. But I really want to be there to show you how to do that. So just getting it set up is good enough. If you'd like to pause the video and write this down, then you are done. So I hope everybody's having a good day, and you continue to do so, and we'll talk again later.